morning, one and all physics students, to another episode of Physics. It's Mr. Finn coming to you from neighborly Northville. Had a couple questions today regarding the hat, Mr. Finn's hat. This is not a Golden State Warrior hat, even though it does say GS on it. It actually says Gong Show on it. I don't know what that means, but the Gong Show, not this video cast, but Gong Show, I don't know. That could be our semester experience without getting together. I don't know. So I don't really know what the answer to that question is, but that is the hat that I'm wearing for this particular episode. All right, second thing. If you are not retaking or you're not taking the Google form today on rotation, you can cut out, because we are not going to do parallel circuits today. We're going to resume that on Monday. Today, I'm simply going to do a small review on rotation, because those students who are doing a retake, or rather an addendum to the rotations test, this is their video cast for that. I'm just going to do the review on that. But before I get to that, let me talk a few things first in terms of protocol. As you guys know, our system is changing rapidly. Reminding you guys that Tuesdays and Wednesdays, those are our Google Meets. First and second hour on Tuesdays, third and fourth hour on Wednesdays at 11 a.m. and 1 p.m. respectively. Prior to the 11 o'clock Google Meet, I will have office hours from 10:30 to 11 for first hour and third hour on Tuesdays and Wednesdays. And then right after, we're going to go before the 1 o'clock time, so 12:30 to 1. That will be our time for office hours for the third and fourth hour on Tuesdays and Wednesdays. So I'll put that up on the Google Doc just to make sure you guys know that that's the case. Okay? All right. Well, let's get started with a little review on rotation. You guys will remember the rotation material was a whale of a time ago, long time ago. And what did we really cover there? 4 or 5 basic things. Rotational inertia, which is the resistance an object has to change in rotational states. Torque. Torques are things that make things change rotation. So if I'm holding this here and I provide a torque, then I'm changing its rotational state. I'm either speeding it up in a circle or I'm slowing it down in a circle. Whatever happens to happen, if you are applying a torque, the angular velocity is changing, the angular momentum is changing. Okay? Angular acceleration. Angular acceleration, that was a change in angular velocity over a time frame. As a matter of fact, I have all these terms written up for it. Why don't we just go to the big board and we'll walk through them one by one. Okay, guys, let's walk through this one by one. We talked about rotational inertia. So this object, like any object, would have rotational inertia simply because it has mass. And anything has a radius that we can define. If we define the radius to this way, in other words, what's the rotational inertia from this point? We would define an axis of rotation first. So before we talk about rotational inertia of an object, we have to talk about what axis we would be rotating on. It would be very different for this item to rotate on this axis than it would be to rotate on this axis. So as you can see, the inertia values would be much different. This would be simply a cylinder about its center axis. But this would be more like a stick about its center axis in the middle of the stick. And the two would be very different. Don't forget about page 157 there to determine the difference between individual rotational inertias for different axes of rotation. But simply rotational inertia is the resistance an object has to changes in its rotational state. Therefore, the more lazy it is, the more rotational inertia it has. You may recall the races down the incline of the ring and the disc. Well, the ring, where most of the mass was on the outside, had a higher rotational inertia. It was more lazy, resistance to change, which means it did not accelerate quickly. It got down the ramp slower, but once it got down the ramp, it traveled longer on the floor because it was able to rotate longer, resist the changes to its state. Here's that definition we talked about. Force times radial distance. But remember, torque is two different things. Additionally to that, it is rotational inertia times angular acceleration. Kind of like force is mass times acceleration. Torque is an analogous feature with inertia, rotational inertia times angular acceleration. Also, force is also change in momentum divided by time. So analogously, torque is change in angular momentum over time. So three definitions of torque. Remember, torques are things that cause changes in rotational states. So in order to get this bar rotating, I need to provide the torque. I need to do that. Otherwise, this thing without a net torque would simply not change its rotational state. So remember that merry-go-round example. When the kids start the merry-go-round moving, they're providing a net torque. When they jump off and they stop the merry-go-round from rotating, they're also providing a torque to the system. Angular velocity. Remember this symbol, omega. That's a radial speed measured in radians per second. And that's just a measure of how fast things are rotating in a circle. Remember, it's not in meters per second. It's in radians per second, or percentages of a circle that it can traverse in any one time frame. Angular acceleration, that's alpha. So radial acceleration measured in radians per second squared. So how quickly do we change the percentage of a circle? How quickly do we change from, let's say, 0 radians per second to, let's say, pi radians per second? If we did that in 2 seconds, we would have pi radians per second, or 3.14 minus 0 divided by 2. And we'd get about 1.57 radians per second squared. So just an example of how to get angular acceleration. Lastly, angular momentum. Angular momentum is kind of like straight line momentum. Straight line momentum was mass times velocity. So angular momentum is rotational inertia times angular velocity. And remember, torques cause changes in angular momentum. Therefore, if there's no change in angular momentum, there could not have been a net torque applied. Okay, guys, I hope that helps. If you have any questions, please email them in. But that's my basic review of torque. I think you guys will have a better time now that you've had a chance to think about things and maybe practice some extra things there. And maybe get some of those questions, some little bit of feedback to the questions you had the first time around. Okay, guys, make sure you dial in on my Google form right around 3 o'clock. I'll keep it open for a few hours there, just in case some of you guys are busy right at the 3 o'clock time. On Monday, we'll start talking about parallel circuits again, and we'll have some more practice on that. Okay, guys, good luck today, and we'll see you on Monday.